So what time is it now in India?
It's 11:29. I
Right.
think it's
Oh,
5.5 hours difference.
yeah, and it's 5 o'clock here. So yep, good. I fed the cat and he's had his food, so that's good.
Okay. Just 1 minute. We have two more students. So one of the student has some issue with connection. So he has connected with someone else's laptop, like he's there. And there is one more student, he's having some login issues. I'll just tell him. Okay. So I guess, John, we'll start. The other student will also join along with
Okay.
one of the students.
Okay.
So we have 8. So over here, you are not seeing two students. That is Chandu and Roshan. These are the
Right.
students. So once you interact with them, you will get to know.
Yeah.
And okay. So thank you very much, John, for accepting our invitation. So we are in dire need of a geology faculty. We have got a few CVs and we are planning to process it. But then till that time, it's good that you are helping us with this course, and that also an interesting topic amongst the 9 of the topics that you had shared. All of them are interesting, let me tell you. But then I discussed with the students also. So we thought, let us go with this particular topic,
Yeah.
composition of Mars.
Hmm.
Okay, so I keep this open up to you, and I will have to go for some 2, 3 meetings and a class that I have. So I'll join in between, but you can go along.
No worries. Thank you, Renita, and thank you very much for having me with you today. I'm aware that there's no geologists in the audience. So if I use terms that I don't explain, please put your hand up. So if you go down somewhere on your screen, you should have a place where you can respond and put your hand up. Please do that. Or put it into the chat, and I'll try and explain, answer your questions that way. But main questions we will leave to the end, if that's all right. So what we'll be looking at today is the composition of Mars. What Mars is made of, how it varies in space across the surface of the planet, and what principles, basic scientific principles are involved in creating that distribution. So what we're looking at then is a basic introduction to rock and meteorite classification. So this will introduce some terms that you need to keep in mind. We'll then do a bulk comparison of the Earth and Mars. We'll look at Goldschmidt's classification of the elements, and I'll be explaining what that is. Don't worry. And then how these things, the bulk composition of the Earth and Mars, the classification of meteorites, the classification of the elements, are related to the formation of the solar system and planets. And then from then we can move on to the actual surface composition of Mars, and indeed aspects of the interior composition of Mars. And then what we've learned about the composition of Mars from surface missions as well as orbital missions. And then close with the question of Mars sample return. So unless there's any questions, we'll move on. So some terms that I'll be using that people need to become familiar with. So when we talk about rocks, such as a granite, and here's a picture of a granite, I just stole it off the internet. We talk about minerals being either mafic or felsic. And these basically mean dark colored minerals and light colored minerals. So mafic minerals are minerals rich in iron and magnesium, and they're almost always dark colored. So we've got mafic, we've got amphiboles here, and we've got, which are the mafic minerals, and we've got felsic minerals are potassium feldspar, calcium feldspar, and quartz. You can look this up later, but at this stage, just remember dark and light. So when I talk about a mafic rock, I'm talking about a dark colored rock, an igneous rock, and when I talk about a felsic rock, it's a light colored rock. No, nothing too fancy there. Second thing to keep in mind is the basic difference between what we call igneous rocks and sedimentary rocks. When we talk about rocks being felsic or mafic, we're talking about igneous rocks, rocks that used to be molten inside the earth and have either cooled into a solid state inside the earth, or they have been erupted onto the surface by volcanoes. And so we have felsic rocks like granite or rhyolite, which are increasing silica content, SiO2, silicon dioxide, light-colored minerals, going down through intermediate rock like diorite and andesite, to fully mafic rocks like gabbro, dolerite, and basalt. And a lot of these rocks are familiar in India through the Deccan traps, which are made up of these rocks. And then ultramafic rocks, very dark rocks, which are composed almost entirely of mafic minerals. Sedimentary rocks, on the other hand, have a very easy classification. They're basically made up of clay or silt or sand, gravel, and these are, of course, from fine-grained rocks all the way up to gravel. And when these sediments, which are laid down in rivers or by the sea or in lakes, or perhaps even by the wind, when these sediments become rocks, we call them claystone, siltstone, sandstone, and conglomerate. One of the things about geology is, although we have a lot of terms, a lot of them, once you get your head around them, are quite simple and straightforward. And so I've got some photos here of fairly typical examples of each of those. So up in the top left here, we've got granite going down to granite diorite, to diorite, and down to an ultramafic rock at the dunite, I think, or a peridotite at the bottom. And on the top, that's top left to bottom left, top right to bottom right, we've got a conglomerate made up of pebbles, a sandstone made up of andesite particles, a siltstone made up of silt-sized particles, and a claystone made up of clay-sized particles. And these terms are applicable right across the solar system and across the universe where there are rocks. So, a granite on Mars, should there be a granite on Mars, will have all the same properties as a granite here on Earth. Now, when we look at the bulk composition of the Earth and Mars, and we get these from the averages of many, many geochemical analyses on Earth. On Mars, we also have samples from Mars. I'll be talking about these later in the form of Mars meteorites. We also have spectral information of the surface from ground-based telescopes and orbiting spacecraft. We can see that the composition in terms of the elements for the Earth and Mars are very, very similar. Both are dominated by oxygen because most of the minerals in there are present as oxides. Iron is very important, magnesium, silica, and then there's varying amounts of carbon, sulfur, aluminium, calcium, and other minerals. But if you want to understand how these elements are distributed on Mars and indeed on Earth and on other planets in the solar system, we've got to get to know Goldschmidt's classification. Now, this is something I wish I'd learned when I was a student, and I only really started coming to terms with it a few years ago. And it's a very, very powerful way of understanding how elements are distributed in the solar system, in rocks, and in everything in between. Now, Victor Goldschmidt was a German scientist in the late 19th to mid 20th century. And he was a geochemist. He studied the chemistry of rocks, the processes involved in, say, the smelting of rocks in mines and in metallurgical plants. And he divided the periodic table, which you all know, into different families of elements, which he called siderophile, iron-loving, lithophile, rock-loving, chalcophile, literally copper-loving, but in reality sulfur-loving, and atmophile, atmosphere-loving elements. And here we see them mapped out in different colors on the periodic table. And how did he come up with this? Well, he came up with it when he was looking at the smelting of copper shale ore, Kupferschiefer ore at Mansfield in Germany. And during the smelting of these ores, he noticed that 3 different liquids developed and solidified: the iron melt, the copper sulfide melt, which he called a matte, and a silicate slag. And you'll see varieties of this sort of behavior in smelting operations around the world. If you were to go to a copper furnace or a zinc furnace or an iron furnace, you'd see a similar sort of distribution of melts. And analyzing these solidified melts, he saw that there were similarities between them and the different types of meteorites. And so he wrote himself, in most meteorites, there are 3 phases present: an iron-nickel metal alloy, sulfide, an iron sulfide phase, an iron sulfide mineral called troilite, which we don't find on Earth except as in a meteorite, and silicates. And Goldschmidt thus reasoned that by analyzing these phases, we would find the relative preference for individual elements and provide a basis for classifying elements. This is a hypothesis he had, and it's subsequently been tested over and over again in terrestrial smelters, in meteorites, in the samples from the Moon and Mars and other bodies. So here we go, the atmophile elements. So these are the ones that are gaseous. So hydrogen, obviously, on Earth, it's not a gas; it's a liquid, but it's a surface volatile compound. Carbon generally exists as carbon dioxide. Nitrogen, we know. And then on the far right, we've got the noble gases: helium, argon, neon, and so on. And these are the atmosphere-loving elements. I think, what have I done? The sulfur-loving elements we find in magmatic and hydrothermal sulfide deposits. So if you go to a copper sulfide mine or a zinc sulfide mine, we'll see these associations of the chalcophile elements. They're copper and zinc, arsenic, sulfur, of course, silver, cadmium, a whole lot of elements that are actually very important economically, and we mine them. Lithophile elements are those that are concentrated in the mantle and crust. And these are the ones we see here in in orange. And they're mostly boring elements, lithium, sodium, potassium, calcium, magnesium, aluminium, and so on. The sorry. Okay, one thing I didn't mention, of course, is the siderophile elements, and they're the ones in red, which end up in the core, right? All the iron-rich, nickel-rich core of the Earth also has things like iridium and platinum and manganese as well, and as well as gold. Now, when it comes to the lithophile elements, there's been some more recent work that has subdivided these families that Goldschmidt didn't go into. We notice, for example, that some will tend to go into the crust and some go into the mantle. On top of that, some of the elements, what we call incompatible elements, don't like going into other minerals. So when you have a molten rock and you cool it down, rather than crystallizing out with calcium and aluminium and silicon and oxygen and magnesium and so on, these elements, these incompatible elements, stay in a liquid form, and they only crystallize out in the very last phases. So that's why they're called incompatible elements. So we don't get them very often in bulk rocks, but only in extremely fractionated rocks. And this is why when we talk in geology about evolved crust, it's very important for understanding the distribution of these highly evolved, these highly incompatible elements. It's only in highly evolved crusts, the last bits of molten rock to crystallize, or rocks that have been remelted, that we get significant concentrations of things like potassium, sodium, rare earths, and so on. So in this very schematic and not to scale cross-section through the Earth, you've all heard of plate tectonics, and you know that ocean crust forms at the mid-ocean ridges and then it gets subducted at continental margins and then gets remelted, at least partially remelted. And into this remelted fraction, we get the formation of highly evolved crusts, the granites, for example, and rocks that are rich in sodium, potassium, rare earths, and so on. And we really only see these commonly on Earth. There is no or very little evolved crust on Mars, on the Moon, on Venus, or on Mercury. Because as far as we know, none of these bodies ever had plate tectonics. And these types of evolved crust rocks, the granites, the andesites, and so on, are common only on Earth. And so that's the first big and perhaps one of the most fundamental difference between the Earth and all the other planets. And it's probably related to the fact that Earth, alone of these bodies, has had oceans for almost all of its life. But we can talk more about that later in the questions. So let's look now at how stars and planets form. If you look out of the night sky, in a place where it's clear, like up in Ladakh or out in the middle of the Thar Desert, you'll see along the Milky Way these dark clouds. And these clouds are clouds of interstellar gas and dust. And these collapse under gravity, eventually form what we call protostars, and then full-blown stars, not just protostars, beginning stars, but full-blown stars. And these are surrounded by a disk of material, dust and gas, and out of these, planets will form. This can be modeled and predicted mathematically, but much more importantly, we can actually look out with telescopes and see these processes happening. So in the constellation of Orion, there you have the Orion Nebula, and distributed in the Orion Nebula, not only a whole lot of bright young stars, but I'm not sure if you can see where I'm pointing with my cursor. We see these tiny little black dots, and when we zoom in on them with a very powerful telescope like the Hubble Space Telescope, and these are all Hubble images, we see that these dark spots are actually very bright, very young stars surrounded by dark disks of dust and gas. The Orion Nebula is a factory, if you like, for making stars. And around most of those stars are disks out of which planets are being formed. So we are looking out at this object, which is several hundred light years away, at the actual process of star and planet formation. And in these disks that we have around these young stars, there are complex processes going on from, first of all, from dust, and they, under the influence of solar radiation, undergo partial melting. They form larger particles that we call chondrules, and I'll show examples of those later, to small grains, less than a meter across, to large grains, which are less than a kilometer across. I personally wouldn't call those a grain, but to an astronomer, these are tiny bodies, and so they call them grains. And these large grains aggregate to form planetesimals, and then these aggregate further to form protoplanets, and then planets. And every one of these steps has been observed out in the universe, and also studied in samples that we have from our own solar system's protoplanetary disk, which we call meteorites. So let's look at all of these steps. So this is a polished, cut surface of what we call a carbonaceous chondrite. So this is a family of meteorites that's quite rich in carbon. The carbon is distributed through clays. It occurs as organic compounds, including amino acids and so on, and has large numbers of these round granules, usually about a millimeter or so across, that are called chondrules. So this is a chondrite meteorite. It's got chondrules. It's a carbonaceous chondrite because there's a fair amount of organic matter. Also in these meteorites are little light-colored inclusions that we call calcium-rich inclusions because, surprise, they are rich in calcium, and also they contain aluminium. Now we can date these meteorites by looking at the ratio of radioactive isotopes to their decay products. And both the matrix, the ground mass, the dark material between the chondrules, and the chondrules themselves are about 4.6 billion years old. But the calcium-rich inclusions are anywhere between 5 and 7 billion years old. They are actually older than our solar system, and they form in the interstellar clouds, and then are swept up into the protoplanetary nebula, become parts of the meteorites, the grains, which then become preserved and end up landing on Earth billions of years later as grains. And when I've held an example of meteorites in my hand of a carbonaceous chondrite, and where I used to work, we had samples of several of these, and you see these little white specks in there. It's quite a humbling experience to realize that you're touching a material that's older than our solar system itself, older than the sun, older than the Earth, older than all the planets that we see. Now, it's worth noting that the majority of asteroids and meteorites are chondritic. That is, they contain these chondrules. And we know that because we can look at the way meteorites will reflect light, and we can compare that with the way asteroids reflect light, and the majority of them are similar to chondritic meteorites. Where do they form? Well, here's the interesting thing. If you go back to the protoplanetary disk, you can see that the disk surrounds the early suns. And as you can imagine, close into the early sun or the early stars, it's going to be really hot. And as you go out, it will get cooler and cooler. And so in what we call the protoplanetary disk, the meteorites, the grains that form close to the star, close to what became our sun, will be poor in water and poor in carbon, because they will remain as gases and stay in the outer part of the protoplanetary disk. A bit further out, outside what we call the tar line, we start getting the organics. And then outside from the what we call snow line, we start finding evidence of abundant water within the meteorites. Water may not be there now, may be locked up in other minerals, but there is certainly evidence in many meteorites, many asteroids, some which we brought samples from back to Earth from using spacecraft, that there was ice and liquid water in these bodies. And as you get into the very outer solar system, we get very ice-rich bodies similar to what we call comets. So how do we go from these grains, which have complex histories, even though they're only a few meters to perhaps a few kilometers across, from there to planets? Well, the next stage is what we call planetesimals. This is a planetesimal in the outer part of our solar system called Arakoth. There's a scale there, 5 miles, 8 kilometers. And you can see that each one of this sort of dumbbell-shaped object is actually made up of smaller chunks with quite different composition and textures. And for scale, there's a picture there of a comet that we visited, a spacecraft, was a European spacecraft, was Rosetta, visited a few years ago. And you know, the average comet is about the size of one of these building blocks of a planetesimal. Comet represents, if you like, a grain, and then these grains are aggregated together to form these planetesimals, which nonetheless aren't homogenized, right? Each bit of them has quite different composition. But above a particular size, as the planetesimals aggregate together, they start melting. And as they start melting, gravity will start pulling that body from a sort of random shape, like the dumbbell of Arakoth, into something that's more or less spherical, like Vesta, one of the largest asteroids, which is an example of a protoplanet. And as I said, the reason why it's spherical, because it has started melting, and just like a raindrop, it starts to pull together into a spherical shape and acquires what we call hydrostatic equilibrium. And it is these protoplanets that very early on in the history of the solar system, 4.5 billion years ago, when they come together, form are planets, like the Earth, like Mars, like Venus. And the end result is we have inside the Earth, as a result of the melting, just like in Goldschmidt's metal smelters, ore smelters, we have a differentiation. The outer layer of the planet consists of rocks like basalt, represented by what we call achondrite meteorites. The mantle, which is an ultramafic rock, made up of ultramafic rocks, is represented by howardites. The core, where the very dense iron and nickel melts have settled to, is composed is represented by the iron meteorites. And so the transition between the core and mantle boundary are represented by this very rare group of meteorites that we call stony irons. So are these quite beautiful mixtures of silicate minerals and nickel iron alloy. The undifferentiated asteroids, composed of chondrites, are the bits left over. An example of these is the asteroid Bennu, that was sampled by the US probe called OSIRIS-REx, and we have quite a few, quite large amounts of this material now back on Earth being studied, and it's composed of carbonaceous chondrites. There are similar asteroids for which we also have samples from spacecraft, such as the Japanese Hayabusa spacecraft, which are composed of ordinary chondrites, as you can see there. So that picture there on the right is of the Earth, but essentially Mars and Venus are similar. We'll have similar differentiation between rocks, mafic rocks on the surface, ultramafic rocks in the mantle, and a metal alloy, an iron nickel core in the center. The Earth, of course, the crust has undergone further differentiation to form granites and granitic rocks that we call differentiated crust, which is largely missing from Mars. So we now finally come to the main topic of today's lecture, the composition of the Martian crust. Now, one of the best tools that we have at this stage for the composition of the Martian crust was obtained from a US-led but an international space mission called Mars Global Surveyor. This had instruments on board, most from the US, from Europe, from Russia, and it mapped using, it took high-resolution photos of the surface of Mars down to a resolution of a few meters. It mapped gamma rays being given off by the surface down to a depth of 30 centimeters, and neutrons being given off to a depth of about 1 meter. The result of cosmic radiation from the sun, from cosmic rays impacting the surface. The HEND and neutron spectrometer measured the neutrons, and the elements potassium, thorium, sulfur, chlorine, there's a typo here which I'll have to fix, and silicon were mapped by the gamma rays. Now, although the photographs obtained by Mars Global Surveyor were at a 3 meter, 4 meter resolution, unfortunately, the chemical information was much poorer. It actually made up of blocks, if you like, pixels of the surface, several hundred, in fact, 300 kilometers across. So very, very coarse data. So when I show you the maps of the surface composition, remember that this information is very low resolution. And within each of those, there may be a lot more variation that we're not currently seeing. So here we have a map of potassium. And very crudely, we can see that there is more potassium in rocks in the northern hemisphere of Mars than there are in the south, although there's areas of moderate amounts of potassium in the south. Mind you, overall, the amount of potassium is quite low. I mean, the highest is perhaps 0.6 or 1%. Remember what I said. Minerals like potassium are concentrated in evolved crust. So there's not much evidence of evolved crust in the potassium map from Mars Global Surveyor. Thorium, another element concentrated in evolved crust. Again, you can see that most the highest concentrations are in the northern hemisphere of Mars, and there's a bit less in the south. Again, very, very little. 0.8, maybe almost 1% maximum, whereas a granite on Earth might have several percent thorium in it, by way of contrast. Iron, slightly more concentrated in the northern hemisphere of Mars, much higher concentrations than, say, potassium or thorium, over 20% in places, whereas the southern highlands are a little bit lower. Silicon, it's sort of blotchy and doesn't really, although there's variation, doesn't really follow this north-south composition or pattern that we see in some of the other elements. Chlorine, again, blotchy. Again, no real concentration in the northern versus the southern hemisphere. Chlorine, as you know, is found in salts. Moves around as salt, sodium chloride. And this shows that the surface layer of Mars is somewhat salty. As you'd expect, the surface of Mars is essentially a desert, and you'd expect any water to evaporate very quickly, leaving dissolved salts behind. Sulfur, again, yeah, moderate amounts, 3.2% maximum, concentrated in a couple of areas. Sulfur may be present as sulfate minerals, which are kind of salt, or may be present as sulfide, locked up into rocks. Note there's a location there called Mer A. Mer A is the Mars exploration rovers, and Mars exploration rover A we now call Opportunity, and that's spent about 8 years, if I remember correctly, 8 years, close on 8 years, driving around the Meridiani region of Mars, right in that orange-red area on the right-hand side, and showed that the rocks there are dominated by sulfate salts, like gypsum, which some people put in their gardens, magnesium sulfate, similar to epsomite, which some people take if they've got upset stomachs. These are found on the surface of Mars and are formed on Mars, just like they are on Earth, from the evaporation of salty water. So some of these areas of Mars where there is high levels of sulfur were once salt lakes early on in the history of Mars. And very large salt lakes. Remember, the resolution of these maps is more than 300 kilometers. So these are areas hundreds of kilometers across, thousands of kilometers across, enriched in salts transported by water. Now, this is the map that caused perhaps the biggest excitement when we got it, and that's the distribution of water. And it shows that, and this is measured not from gamma rays like the others, but from neutrons. When cosmic rays bombard the surface of Mars and the moon for that matter, slow neutrons are given off and can be detected by appropriate satellite instruments, and they are detectable down to a depth of about 1 meter below the surface. So the areas where you got warm colors, oranges and yellows, have water in them to at least 7%. This is one particular instrument called HEND, which is a Russian one. A different instrument called a neutron spectrometer, which is the American instrument, mapped it in somewhat more detail and showed that the colors are the other way around for here. The highest the concentration of water, the colder the colors. You can see that the equator and near equatorial regions down to about 30 to 50 degrees north and south are fairly low in water down to a meter depth. But north and south of that, we can have up to 70% water in the top meter of Mars. Mars is an icy planet. And this is really important when we talk about the early history of Mars. We see lots of evidence for water moving around the surface. We see lakes, as I mentioned, in the forms of salt minerals, former lakes. We see dried up river valleys. And for a long time, people said, well, where has this water gone? And the answer is it's gone into the soil. It's gone to the subsurface. And we get these subsurface ice deposits. They're also important because ice, if you're interested in astrobiology, ice is a very good way of preserving biosignatures. So if we're going to look for biosignatures on Mars, one of the very good places to look is in these ice deposits in the northern and the southern hemisphere. Ice is also really important when we're talking about potential human visitors to Mars, because of course, ice we can turn into propellant for people to come home again. It makes logistics of traveling to Mars a lot easier. We can use it to, we can melt it to make water for crops and for astronauts to drink. So this image and the hand image before it are really, really important in terms of showing that Mars was once potentially habitable when this ice was liquid water, and also shows that it is potentially habitable in the future for humans, where we can extract this ice as liquid water to support human occupation. Now, we can find rocks from Mars. 1970, in the 1970s, a small group of 9 meteorites that we call achondrites. They didn't have chondrules in them. They were basically igneous rocks belonging to 3 separate classes. Were all recognized as coming from the same body. And this was on the basis of their chemical similarity. They also contained iron oxide, red iron. And people said, well, the only planet in the solar system that has red iron in large quantities on the surface is Mars. Maybe they come from Mars. And then 1983, people compared the ratios of noble gases in a Mars meteorite, and they show, and this is in the graph on the right there, showed them as identical, almost no difference whatsoever between these meteorites and samples from Mars measured by the Viking lander. And so this little group of 9 basaltic meteorites turned out to be far more important than just being ordinary meteorites. They're actually samples of Mars. But how do they get here? Well, basically any meteorite that strikes the surface of Mars and makes a crater more than about 50 kilometers across, like the Mojave crater here, is energetic enough to blast fragments into orbit, not just into Mars orbit, but into solar orbit. And a tiny fraction of these will intersect with the Earth and fall as meteorites. And back then, only 9 Mars meteorites were known. As of last week, 208 examples are now known. And nearly all are these basaltic meteorites we call shergottites, which are basically basalts and similar rocks, somewhat more coarser-grained dolerites and gabbros associated with them. Here's a picture of them. If you didn't know that they were from Mars, you would just say these are very typical mafic rocks, similar to what we find in the Deccan Plateau, similar to what you find in many locations on Earth. Some other compositions are known. On the top left there, we have a breccia. A breccia is a rock that's made up of fragments of other rocks. This is a very, very unique Mars meteorite. It's the only Mars breccia known, so it actually represents the surface layer of Mars. We find ultramafic rocks, a pyroxenite there, a chazagite, and a narcolite. These are all rocks with very little light-colored material in them and very rich in dark-colored minerals. Allen Hills 84001 at the top right there is a very, very important meteorite because in the 1990s, people found traces of carbon in it, some of which looked like it could have been in the form of fossils of bacteria. That rock has now been analyzed till no longer exists. And at the moment, most people think that those were not fossils, but it's a very interesting Martian rocks, and it shows that actually proving that Mars once had life might be a lot harder, even if we think we find fossils than people might have originally thought. In terms of ages, this is looking at the different families of shergottites, and they actually form into discrete ages. Nearly all of them are quite young, 150 million years old down to about 200 million years old. Almost all are younger than 1 billion years, and only 2 examples are older, in this case 2.4 billion years. So there was young volcanism happening on Mars, geologically young. 150 million years ago is only just a little bit older than the some of the oldest rocks in the Deccan basalts. So the time when there were dinosaurs on Earth, there were volcanoes active on the surface of Mars. When there were trilobites swimming around in the Martian Sea, there were volcanic rocks forming on Mars. But another way of dating Martian meteorites is we look at their ejection ages, because when a Martian meteorite is shocked and blasted off the surface of Mars, that too leads a geochemical trace in its isotope ratios that allows us to date them. And we can see that all of the Martian meteorites that have been analyzed in this way were blasted off the surface of Mars in the last 20 million years. So this means that if we look for big Martian craters that are very young, and we compare the composition of the rocks where those craters are with the composition of the meteorites, we might be able to tell where some of these meteorites come from. This is another plot, and again, it shows that the very young meteorites, well, let me backtrack. The meteorite ages tend to cluster, as do their, and they're quite discrete in how they cluster. So very young ones, or very young Martian rocks, are all ejected quite recently. Some of the older ones are also ejected as a group. So these represent individual impacts on the surface. And Allen Hills 84001, the one that was supposed to have fossils in it, is not only a very old Martian rock, but also one of the oldest meteorites that we have in terms of when it was ejected from Mars. Won't worry about that. I'll come back to some of these questions in a minute, but let's now look at photos of Mars from surface missions, because these photos show that much of the surface geology of Mars is made up of rocks that aren't going to survive being transported as meteorites. They're too fragile. It's like going through what's left of a house after an earthquake. What survives are things that are really strong. Fragile things like glass and so on will just be reduced to fragments. And same on Mars. So when we look at the photos from Mars landers, Mars rovers, we see all sorts of fragile lithologies, which are actually much more interesting than just sort of boring old basalt. We see breccias. So here we have examples of breccias. Remember, a breccia is a rock that's made up of pieces of other rock sort of glued together. And here we have examples. And these are generally the result of impact processes. And we have only one example of a Mars meteorite that's an impact breccia. We find all sorts of sedimentary rocks, which are physically quite weak and would never survive being transported. We have mud cracks formed by the drying out of fine-grained sediments in a pond of water of Gale Crater. We have those strange moles in the top right there, elongated holes in the rocks where salts have been leached out of the rock, leaving the shape of salt crystals behind them. And we have concretions, little ironstone, hematite in this case, iron oxide balls, which have grown in the rock as a result of fluids coming through them. I mean, people would probably give their eye teeth to get samples of these, but we'll never see these in Martian meteorites. We have cross-bedded sandstones. You see those in many places in India. They can be formed in large rivers, for example, like the Ganges and Brahmaputra, in the big sort of sand bodies that you get in these rivers. And conglomerates, which we get in high energy streams where pebbles are washed down and cemented together. We find all sorts of very diverse igneous rocks, some of which are pyroclasts, volcanic ash, glued together. So at the top left there, we've got, where it's arrowed, we've actually what we call a bomb. You've got layered volcanic ash, and you've got a rock that has been dropped down into it and pushed the underlying layers down beneath it as it's come down like a plop. Again, too weak to find in the meteorite. Altered basalts of various type, granites, granite-like rocks, komatiites. We do find some of these in meteorites. We have yet to find a granite. We find highly altered rocks. Rocks alter through weathering, forming weathering profiles like lateritic weathering profiles. They are altered in hydrothermal systems beneath fossil hot springs, and we see examples of both on Mars. But if you go and look at a weathering profile, if you go and look at the altered rocks around a hot spring, they're very weak. So we'll never see them in meteorites. More hot spring deposits. On the left, we have one in Chile, and these strange knobbly fingers of rocks growing just a few millimeters across, growing in the hot spring pools. On the left, we have a Martian hot spring, a fossil hot spring. It hasn't been active for well over 1 billion years, with identical textures and identical composition. And what's really intriguing is that these finger-like growths in terrestrial hot springs are at least partly due to the activities of cyanobacteria and other microbes growing in the water. So if people want to say, what do I think is the best evidence yet for possible life on Mars? I think it's these rocks from home plate in Gusev. But we'll never see them in Mars meteorites. And the ultimate in fragile material that we'll never see on Earth in a Mars meteorite is ice. Top picture there is a picture in Viking. Viking 2, we can see those low troughs. Here's one coming through here. There's another one coming through here. Another picture at the bottom here from the Phoenix land, and we see those troughs form these polygonal patterns. And that sort of texture is very typical of areas with ground ice. Parts of Ladakh in the very high mountains, you'll see similar textures. And when the Phoenix lander looked underneath it, it saw it photographed where the dirt had been blown away by the landing rockets. And underneath, in the bottom left there, we had this white ice. We saw ice as well on the bottom right there when it dug a trench into the soil. Segregated ground ice on Mars, just like we saw in the hydrogen data from the HEND and neutron spectrometer on Mars Global Surveyor. Here we have proof on the ground. Astrobiologists, geochemists would give their eye teeth to get hold of some of this ice, but we won't find it in meteorites, of course. To do that, we need to actually bring samples back from Mars. And plans are underway to do this. And there's two ways we can do that. To get these samples, these hard to get samples, we can either do it robotically, and both the US and China are planning at the end of this decade to bring samples back from Mars. Trouble is, only about a few hundred grams in each case, which isn't much. Geochemists can do a lot by it, but you imagine trying to distribute a few hundred grams around several hundred geochemists around the world in many different countries. They're not going to get very much to work with. If we want to have lots of samples from Mars, we need to send people. Send people to Mars, we'll get back hundreds of kilograms of very diverse material. And that's a bit further away, perhaps 10 years, perhaps 20 years down the track. But I think that is when we will really start to understand the composition of Mars and its implication for how the planet evolved and for finding life there, either past life or perhaps even present life. So it's now open for you and your questions. Again, if there's any terms I used that aren't familiar, I'm happy to explain. If I talk too fast, I apologize, and we can go back over some material if you want.
Hello, sir. So,
Hi,
can you hear me, sir?
I can, yes.
Yes, sir. So, I have a few questions. The first one being, you mentioned chalcophiles, the one sulfur-loving elements. They are associated with magmatic and hydrothermal systems. So, the first question of like a broader question is: are these chalcophiles do they occur in do they occur naturally, like other than magmatic or hydrothermal systems?
Yeah, well, they are concentrated in hydrothermal systems and some magmatic systems. I mean, you can pick up a lump of soil from your garden and you can analyze it and you can find traces of, say, copper or zinc or arsenic or whatever. But to go from, say, parts per million, which is what you'll find in most soils, to percent concentrations of copper and zinc and lead and arsenic, you need to go to a magmatic system or to a hydrothermal system.
Right.
Yeah.
One more question, sir. I was reading this paper about Puga hot springs. They did a chemical analysis on Puga hot springs.
Mm.
They found hydrated borates, which are lithophiles, and hydrated sulfates, which are chalcophiles.
Mm.
But both of these are associated with a sort of hydrothermal system. That's what hot springs are. So
Yes.
my question would be, in an extinct hydrothermal system, a hydrothermal system that no longer exists, like let's say on Mars in an early time, how do we identify these extinct hydrothermal systems if there are lithophiles that also are related to hydrothermal systems, and there are chalcophiles also that are related to hydrothermal systems?
That's a very good question. Um, Actual hydrothermal systems on Mars we have found, up to now, we have found by accident. So there's one that was called home plate, where they had those funny little finger-like projections. The rover drove right over the top of it. One of its wheels was broken and it was dragging it through the ground, and it actually exposed the material. So that was very accidental.
Yes, it broke the sulfur deposits during while it was moving there.
Yes, yes. So because these hot spring systems are typically quite small. Even a big hot spring deposit, the alteration around it is no more than a few kilometers or even a few tens of kilometers across. But remember that geochemical data we have for Mars is hundreds of kilometers. The scale of the smallest thing we can see is hundreds of kilometers across. So this is why we need to get down on the ground to get ground truth. On Earth, if you're looking for fossil hydrothermal systems, if you're looking for a fossil, a copper deposit, for example, we can use aircraft. And we can get spectral information from aircraft. And of course, we can go over it, drive over it, walk over it. And I've in a previous life, I did that in South America and the Philippines. I was working as an industry geologist. Now, what's interesting about some of the Martian hot springs and why Puga is such a fascinating place is, as you've said, it's rich in boron. This is quite unusual. Not many hot springs on Earth are rich in boron, but some of the ones that we found on Mars are. And some of the very earliest hot springs we have on Earth, from the Pilbara region in Western Australia, are also rich in boron, and these contain the earliest evidence that we have of life on Earth. Boron appears to facilitate the synthesis of RNA. So it's possible that the very earliest life on Earth is associated with boron-rich hot springs, and that's why Puga is a real treasure for people interested in astrobiology.
Yes, thank you, sir. That answers my question.
Any other questions? I wonder if people went to sleep. Oh, there's someone. Hi, Ranga.
Hello, sir.
Hi.
Such a fruitful talk we have. Can you detail in the global composition of Martian crust? Like
The composition of Martian
crust.
crust. The overall composition of Martian crust is basalt, right? It's like basalt.
Yes, sir.
But there will be variations within that. Some parts might be more like be richer in silica. Some will be richer in iron and magnesium. But if you want to take the average for the whole planet, the surface of Mars is essentially basalt.
That does mean, sir, that it is younger than it is younger, but because basalt means younger age.
Not necessarily. I mean, some of the oldest rocks on Earth started out as basalt. I mean, some of the basaltic meteorites on Mars are, billions of years old. But basalt can also form, in volcanoes while we're talking. Volcanoes in Iceland or in Hawaii are erupting basalt. So the composition does not necessarily mean they're young or old. It's like, we can find people of every age, from little babies down to people who are even older than I am.
Right.
Thank you, sir.
Any other questions?
Hello, sir.
Hi.
Hello. It was a nice talk. I really enjoyed it. So I have a question regarding what could be the major constraints to grow crops in Martian soil?
I think probably one of the biggest constraints would be salinity.
Uh-huh.
You saw that I showed the maps of, say, of chloride distribution, which is a bit high. Now, different crops have different levels of tolerance for salt.
Yes.
We can also, because we'll probably be growing things in pressurized greenhouses, the amount of soil will be fairly small, so we may be able to leach the salts out of that using water from ice, and having washed some of the salts out, we can then condition the soil so the crops can be grown on it. But I think the only way we can really find out is by experiments. So I'm fairly confident when we send people to Mars, in addition to people studying the geology of Mars and looking for signs of life and so on, there'll be people who'll be doing experiments, starting off at little greenhouses, growing plants in Martian soil and seeing what needs to be done to perhaps improve the quality of that soil. Because basalt soils on Earth are generally
Yes.
quite fertile. So if we can wash the salts out or find areas with low salt concentrations, then I think the plants will do quite well.
Yeah, sir. Thank you. That
You're
answers
welcome.
my question.
So I got one more question, sir.
Yes.
Yes, sir. Sir, recently came up on this on the NASA website regarding Perseverance finding this olivine and a few other mineral inclusions in a rock named as Sheava Falls.
Yeah.
Yeah. So as we know, olivine is something that we associate with hydrothermal systems as well.
Yeah.
Yes. So my question is: are these minerals that are associated with hydrothermal systems, are they always exposed? Because this Sheava Falls, this olivine was quite exposed on the surface of the rock. So, so what makes them form in that particular region where they form?
Yeah. So, I've got a glass here, right? And it's sort of a cylindrical shape, slightly tapering, going down this way. And then I'll put a piece of paper over the top. So, this is the surface of Mars, and a hydrothermal system will be a pipe or body going down below the surface. And essentially what the Mars rovers and landers and any astronauts or walking across the surface will see is what's exposed on the surface by erosion on the surface of Mars. If they want to see what's happening deeper down, they'll have to dig a bit of a hole or get a drill rig and drill further down on Earth and down into the Martian crust. And that's exactly the same as how we work on Earth. If we, geologists like myself, we map the surface geology. We can only see what's there. If we have satellites or aerial photos, we can only look at the surface. If we want to go below the surface, we either drill or we do geophysical studies. So on Mars, if we find evidence of hydrothermal processes, like that example, Perseverance, and we want to go back and look at it, we need to do geophysics, looking beneath the surface, and then, drill a hole down into it.
Right, sir.
And if we're drilling a hole down, you need tons of equipment. So to go any depth, you're looking at crude missions. I mean, a little robotic drill might be able to go a few tens of centimeters to perhaps a few meters. The Chinese probe, Zhanghu 5 and Zhanghu 6, that brought samples back from the moon. They drilled down about, first one drilled about 1 meter, the second one drilled about 2 meters. But it's very difficult to go much deeper than that using robotic technology. Things get stuck.
Right, sir. Thank you, sir. So, can you talk a little bit more about veins on these rocks, the ones that you showed on mud cracks as well? Like, how do these veins form?
Okay. The veins are made. It's a two-stage process. Basically, veins occur where there's a crack. Right. The rock breaks, and if there's water under pressure that's able to keep the crack apart, water will flow along that crack and will precipitate minerals in it. And those minerals are the vein.
Right.
And that process can happen on the surface or near the surface. It can happen at depths of hundreds of meters, even kilometers inside the Earth and presumably Mars as well. And by looking at the chemistry and mineralogy of the veins, have I got an example here? No, it's in the other room. We can tell a lot about the chemistry of the fluid that deposits them. So, for example, a vein that's rich in calcium and carbonate will tell us that the water will be highly alkaline and will be carrying calcium and carbonate in solution. And it's also possible from looking at the mineral phases to work out the temperature at which it has been precipitated. So veins are very good tools for working out the conditions under which geological processes are happening.
And these veins also have astrobiological implications.
They
like
can do.
importance.
Not every vein does, but if, for example, if the vein is being formed by fluids that and at temperatures compatible with life, they could be. So there are veins on Earth which contain evidence of fossil microbes that go down hundreds of meters, even kilometers in the Earth, because they're nice little microhabitats for them. Other veins are just boring veins, and they're just sitting there not doing anything. And we have to look. I mean, all of these things, you have to look to see if they've got that, that evidence that you're looking for.
Right.
I mean, some veins form at very high temperatures. In particularly those associated with hydrothermal systems, they might have temperatures of hundreds of degrees, and obviously you're not going to find any evidence for life in those.
Right. Thank you.
No worries. So Renita, if there's no more questions, perhaps we can wrap this up. If people think of questions, email them to Renita if she's willing, and she will forward them to me and I can answer them, or at least try. Is Renita still here? She's muted. She may be off somewhere else.
Maybe if there are no more questions, maybe we all can introduce ourselves.
That would be lovely. It'd be good to see your faces, and yeah. So yeah, start
So,
with you.
yes, sir. So my name is Himanshu Deka. I have a biotechnology background actually, bachelor's in biotechnology. But since I've come here and been introduced to this geoscience, planetary science subject, I have been more interested in this. I have found my calling. That's what I can say.
Excellent.
Uh, for this, my interests lie in hydrothermal systems, but especially the ones that are generated by impacts. So impact-driven hydrothermal systems,
Mm,
and I am trying to link that with astrobiology.
mm.
And my main interests are Mars, uh, Titan, and
Yes.
other planets as well.
Yeah.
Yes, sir. As of right now, I am doing a review paper, a review, basically a literature review, and trying to come up with a review paper that would basically do a comparative analysis of terrestrial craters, Martian craters, and craters on Titan. Uh,
Mm, mm,
and hopefully in the future, I'm trying to learn the analytical methods of identifying hydrothermal systems via,
mm,
mineral analogy,
mm,
mineral analytics, and also I'm looking into modeling options that are possible for to see if what factors an impact generated hydrothermal system could create for life to exist.
mm,
So,
mm. Yeah, yeah. I mean, the bigger the impact, the more long lasting
yes, sir.
the hydrothermal system can be. And uh, I've been to Lonar in central Maharashtra, and that's got some signs of hydrothermal systems, but they were not particularly long-lived because it's not that big a crater.
Yes, sir.
I think some of the other craters in India, there's only there are only two, I think, known that are quite large. It might be worth looking at those. Um, a number of years ago, I went to Devon Island and the Horton crater there, which was 22 kilometers across, and that's certainly
Yes,
got evidence of long-lived hydrothermal systems. Um, so once you're getting into the 20-kilometer or larger crater, then it becomes very interesting from a habitability point of view. Mm.
yes, sir.
Mm.
That's what I even found for Holden crater and Chicxulub crater as well. That those
Yeah.
are
Oh, yeah.
much
Yeah.
long lived.
Yeah. Yeah.
Yes, sir.
Chicxulub crater, of course, is the grandfather or grandmother of all big craters. Yeah. Mm. Anyone else want to introduce themselves?
Hello, sir.
Hello.
My name is Ranga Babu. I have the bachelor's background in the maths, physics, and chemistry. And after coming here, I actually I'm interested in the astrochemistry, which
Mm.
is a low temperature astrochemistry
Mm.
and a stimulation of interstellar ices in the laboratories
Mm.
with the using of vacuum physics and surface chemistry. And I want to see how the interaction of molecules with the surface of the ice, which
Mm.
which have the surface chemistry,
Mm.
and there's those simple molecules how they converted into the complex organic
Mm.
molecules.
Mm. Mm. I think that's a very interesting topic, particularly for the outer solar system
Yes, sir.
and comets. I know very little about it, so I'd be fascinated to hear more from you. So, yeah, I mean, the surface chemistry of say Titan or Enceladus.
Yes, sir, absolutely.
Yeah.
One of Indian PRL research laboratory, physical research laboratory, they found the ozone layer in the Callisto, which is the largest satellite of the Jupiter. And there is a Bala Sivaraman, sir. He's a scientist in the PRL. He's doing the present research on the tardigrades, which is a biomolecules.
So yeah, look, I mean, I'm a Mars person, but you know, the number of possible places of great interest for astrobiology in the outer solar system, you know, greatly exceeds the number of areas on Mars. So much harder to study, of course, but work such as yours would be very interesting and very important.
Thank you, sir.
Good afternoon, sir.
Oh, hi.
Hi, sir. And it was great talk. My name is Sharmila, and my background is I'm done my bachelor's in electronics and communication engineering, and now I'm doing my master's in astrobiology here. My background is from technical background, and I involved in biology and geosciences. It was interested in me, and also I interested in radio astronomy and radio techno signatures, and also search for extraterrestrial intelligence. I really fascinated about it, and I doing my internship, and I want to do my project in that radio technology side, and also I interested in SETI, like search for extraterrestrial intelligence, and also I want to develop an antenna that is used to reduce the interference. So I want to do in that way radio astronomy.
Fascinating. I mean, I just sort of stand in awe of what people like you are doing, and I don't really understand the technology, but yeah, it's very fascinating. Indeed, if we don't find the signs of intelligence, we will learn a great deal about um, uh, different aspects of the universe and other planets, interstellar clouds, and all the rest from this radio science. So that's really great.
Thank you, sir.
Hello, sir.
Oops. Hi, Ravina.
Hi, sir. That was a wonderful talk. Thank you so much for that. And I hope you're doing well. I think it's quite late there, right? At night.
Oh, it's not too bad. The sun's still shining. I've got to get the washing in soon.
Okay. I've done my bachelor's in zoology, and currently I'm interested in on effects of space flight on human physiology. I'm also
Ah,
doing a term paper on that. I'm writing a review paper on that.
mm,
And specifically, I'm interested in effect of space flight and microgravity and radiation, everything on the human
mm.
nervous system. I
Okay.
believe that is one of the most important things when we plan
Mm,
missions,
mm,
long-term missions, short-term missions.
mm,
It's quite important to learn how that affects our central
mm,
nervous system on as a coherent unit altogether.
mm,
So
mm,
that is what I'm working on currently.
mm, mm. Okay, so you are working with ISRO, or you are in ISRO?
Uh, um, I'm currently writing my term paper with Vinod Kannan sir, VK sir, and we have applied for internships in HSFC. The department has applied. I've yet to hear it from them, so I'm hoping to do my internship with them. Yes.
Great. Great. Yes, I'm very interested in the human space flight because, yeah, I want to see people walking on Mars and other planets. And yeah, anything that helps us in that goal is fantastic.
Yes. Thank you.
Hi, Anita. You're back again.
Yes, yes. I guess we are done almost, or we still
Pretty
have
well
any
done.
questions?
We're just filling in by people who want to. They're introducing themselves, and quite a few of them have, and talking about their own interest and their own background,
Okay.
which is really great. If you want to wrap it up, yeah, I'm cool with that.
Yes. So if you all have any more questions, then I shall share the email ID of John, and you all
Yes.
can connect to him directly.
Yes,
Okay.
that'll be great.
Yes, yes. So, John, thank you so very much for this session. And I'm sure students have definitely loved you. So we previously had Annalie who had taken the session.
Yes,
So I
yes.
think now it's Jen who's still left with us. But thank you so much for chipping in the last moment to help us with some aspects related to the composition of Mars. And I shall share your email ID with the students also. And if they want to connect anything directly, they will definitely connect.
I'll check my presentation and then I'll send you the latest version.
Yes, yes, no issues.
Yeah,
Yes.
cool. So what I said before was a one from a couple of years ago. So I've updated a bit. So yeah.
Yes, sure. Okay.
All right.
Yes.
Goodbye,
Thank you
everyone.
so much.
Thank you so much for listening.
Bye.
Bye.
Thank you.
Thank you, sir.
Bye.